I think that we may have did we just start now? I'm gonna back up a little bit here because I think we just kicked in to bring everybody in from the lobby. So really quick again, I'm Jason Blum from GPL, joined today by Nick Allevato. He's our Senior Cloud and DevOps Engineer. Again, I've worked with Nick for about 10 years in various capacities. He's a phenomenal resource. He's done a lot of cloud migrations, cloud rendering setups, and cloud hosted workstation GPU projects for folks. So he's a great resource to lead our call today. Those of you who don't know about GPL, really quick in a nutshell, I'm not sure if some of this came through when I was speaking before. We are a systems integrator. We focus largely on media entertainment, but we've done a lot of work, especially recently with COVID, in other verticals where we have really heavy GPU intensive, graphics intensive workloads. A large part of that has been transitioning those folks from purely on-premises workload paradigm into more of a hybrid cloud or a fully public cloud kind of setup, moving their workstations, their computes, and their storage into public and private clouds models. And managing those kinds of cloud models is what we're going to be talking about today. Again, Nick is our Senior Cloud and DevOps Engineer. He's going to be talking about moving workloads to the cloud, and then what are the modern methodologies for managing those workloads. Because it's not about just getting it there, it's about how you handle it and scale it and operate it once it's there. And Nick has truly had a lot of experience in that. He's going to be a great resource to go over all of our topics today. We're going to hit 6 main points today. The first one is going to be, what is a good entry point for cloud adoption? When does it make sense to make that leap from on-prem to some form of public or private cloud? Then what should engineers be thinking about when they're considering a cloud initiative? When it's time to get down to brass tacks of getting those cloud mechanisms up and running, what is that tipping point and what technical issues need to be considered when you're doing that? From there, we're going to pivot into what modern methodology means to that. What exactly is it and how is it used for cloud? How is everything as code implemented to help you manage and scale the cloud configs that we're building? We'll then talk about how modern methodologies help you manage things better, how it makes your life easier for the business and for engineers. And then we're going to look a little bit at what a cloud-based virtual desktop infrastructure actually looks like. We're going to talk about the design, implementation, and the management of cloud-hosted VDI, especially as it relates to M&E pipelines. And then finally, how do we use modern methodology to manage all of these aspects? And we'll dig into how it all gets tied together and ideally makes life easier for everybody from business stakeholders to engineers to end users. So with that, Nick, I think that sets you up pretty good to kick things off. I'm going to turn it over to you and you can dig into the meat of this.
Awesome. Thank you for the intro. Nick Allevato, a Senior Cloud and DevOps Engineer here at GPL. I've just over a decade in the M&E space. As Jason mentioned, I've worked with him in various capacities throughout my tenure in this industry. Primarily worked in VFX, animation, and editorial, though those are somewhat converging, and there's mocap and some other disciplines that have materialized in the last decade. We can adapt to those as well. I specialize in storage, farm, switching, routing, software lifecycle management, have installed Isilon clusters, QNAPs, NetApps, Cumulos. I've extended those to the cloud. I've worked with infrastructure providers and the industry leaders for a lot of the technologies used in the M&E space. I also have about 5 years experience in the software as a service space. I worked for an asset management company in the media entertainment that was providing a asset management software, and so worked on the inner workings of applications like that, data flow, multi-region, multi-site, set to script or script to set to screen workflows. So I have a lot of experience with software development. Also have a lot of experience with real-time multiplayer games, which interestingly enough is a pretty demanding resource for cloud, a pretty demanding application, I should say. I've shipped several dozen cloud applications. Shipped means either a show has been developed and delivered using infrastructure that I had a direct hand in designing and implementing. Shipped also means in production with hundreds or thousands of requests per minute or per second, multi-region, highly available applications. I've worked in, on, or around many movies, commercials, spots, branding packages, augmented reality applications, and more. I personally love technology. I have a personal passion and a professional passion for technology. I have a small side passion for writing somewhat pointless web applications and little tools for myself. I love code. I love writing it. And I also love, interestingly enough, I love cleaning. And in my professional capacity, I've entered into many messy environments and infrastructures, and when I leave them, they're clean. So I do personally like taking something that is chaotic and giving it order. And so with that, we come to cloud. So to lead off, let's talk about what is a good entry point for, or how do you start a cloud adoption initiative? We like to say that everybody has an entry point. From a simple website hosting to a complex multi-region infrastructure with data sync and artists in multiple regions, cloud can support nearly every workflow that we want to throw at it these days. Infrastructure can be composed to mirror what we've all worked with over the years, from networks to subnets to servers, storage, licensing. All the infrastructure can exist in the cloud. So cloud is very flexible these days. The platforms are very mature, and we are able to build infrastructure for the media and entertainment industry that is just like what we've all worked with over the last decade. So the best way to start with cloud is to simply start. There will always be some low-hanging fruit in a business that will enable engineers to either dip their toes or jump right in. And that adoption comes with a learning curve. But with the guidance and experience of a cloud partner like us or others, the difficulty of that curve can be reduced or even flattened. There's a lot of materials out there, and those lessons and learnings from others can help the anticipation of the learning curve happen sooner rather than later, and you can build to the spec you need. You can build to what the business needs, and you can start off on the right foot. A lot of cloud projects that we inherit from customers went the wrong direction because they didn't use a modern methodology to begin with. And we'll get into exactly what that means in a few here. So in terms of engineering, what should engineers be thinking about when they're considering a cloud initiative? I like to approach cloud initiatives from the business need. We like to approach it from the business need. The business need can vary. It can be a cost goal. It can be a flexibility goal. It can be an agility goal. But engineers need to be aware of the business need. The business need is the bottom line goal of the business. Is the business concerned with the latest technology, or is it more concerned with cost? Is the business concerned with agility, flexibility, scalability, or is it more concerned with reliability and uptime? The business it could be concerned with some redundancy, and the answer may be one or more of those items and some combination of them as well. And so knowing the goals of the business through the stakeholders enables the engineers to focus on the goal at the end of the day and use the cloud technology and even on some on-prem technology to accomplish that goal. Something that is very important for engineers to consider is talent, experience, and timeline. The talent means the experience of themselves or other team members in terms of cloud. Experience can be a mix. Timeline is also very important. If a business needs something in the short term versus the long term, there can be less technical debt in the short term, and things can be developed a little bit more slowly, and the result at the end of the project would be acceptable and also perfect in terms of what we would want to accomplish from the engineering side. If the timeline is a little bit more compressed, there might need to be some trade-offs made, which is common, but those trade-offs can be planned. somewhat. So other things to consider is there an existing cloud footprint? That cloud could be a tier 1 infrastructure provider like AWS or Azure. The cloud footprint could be a web hosting service. It could be one of the second tier data storage providers like Wasabi or any of the others, Backblaze, and that don't offer full infrastructure, but they offer some infrastructure, and the business might already be taking advantage of that. Considering those is important because cloud, we are still susceptible to infrastructure sprawl and other challenges that come with a rapidly changing or just changing infrastructure, and we want to make sure we think about those things at the beginning and make a decision that will allow the engineer to be successful in accomplishing those business goals. The existing infrastructure complexity is also something that should be considered by the stakeholders and the engineering team as well. These complexities can be varied, can be TPN networks, can be license servers, authentication, existing VDI solutions, existing cloud, maybe there's a hybrid on-prem, VPNs can be involved. Also things like the studio, these are multiple regions, are we multi-site, things like that. So, and then another really important item is there any existing technical debt? Technical debt are things that the engineering or IT teams did not take care of in the past and will come up as something that needs to be dealt with in the future. You can think of technical debt just like a mortgage. You can take out a loan on a house, but eventually have to pay it off. Technical debt is the same thing, and that's not exclusive to IT or systems administration. It's a term that comes from software development as well, where a developer might be writing some code, and that code, they decide to do something shorter rather than better. That's a fair trade-off. Just need to note that and have an idea of how deep that technical debt is. A deliberate consideration of these ideas will give the engineer both the confidence as well as the ownership of the initiative, enabling personal responsibility to drive success. And so an engineer needs to care about the project, and by understanding the inline goal of the business, they're going to have a personal investment in the success of that initiative, that project. They're going to want to deliver, they're going to want to explore naturally, and they're going to have a full picture of what they're trying to do, which ultimately will help everybody at the end.
Hey, Nick, I got a really quick question. Just where have you seen a lot of success when you're discussing cloud adoption with folks? Are you seeing a lot of success talking to the business stakeholders or the technical stakeholders? Like, who tends to drive those decisions in your experience in most cases?
Sure. You know, from my perspective on the design and implementation side, I think stakeholders tend to drive the initiative. They drive the goals, whereas the engineers are more concerned with the specifics, the complexity of infrastructure code. Exactly what API endpoints we might be talking to, sort of the nuances of it. So I definitely say that there's a little bit of a hybrid between, you know, engineers are stakeholders as well. If the project isn't successful, the engineer is not successful. If the engineer isn't successful, the stakeholder isn't successful. So sharing that responsibility between the engineering and the stakeholder, almost making them equivalent stakeholders or equivalent in responsibility, is something that I like to push for, and that we see pairs well with successful projects. When everyone's go ahead.
Sorry, go ahead.
No, that was it.
How about some of those low-hanging fruit projects that you were talking about before? Like, what are you seeing? Like, what's something that an engineer could walk away from this call from and think, okay, that makes a lot of sense here. This is something that we can really get underway with minimal effort and minimal risk, but really have some significant impact in at least getting that beachhead established and then being able to move forward from there.
Yeah, data distribution is a big one. Virtual desktop is another. Data distribution is really nice because you can leverage the cloud providers' internal network mechanisms. So if you need to replicate data between regions, you have that basically native in the platforms, and you can start moving data within a week or two at most. You can front it with either Aspera, Signiant, transfer server, custom, or even some FTP solution that has a web UI. So there's a lot of flexibility there on running those services in the cloud. And then on the VDI side, the virtual desktop side, I think the flexibility of the virtual desktop side is the very rapid provisioning that can come up. So as we're going to go into later, this last year, there's a huge push across the industry for this, and the ability to spin up the necessary infrastructure and not be constrained by a traditional on-prem infrastructure made for very quick turnaround and adoption for and deployment for virtual desktop for customers.
Yeah, there's been a lot of focus on virtual desktop at all the major clouds now, especially even Azure and Microsoft doing Windows workstations and GA now. But one of the issues that we see there with a lot of folks, and I think you might agree, is that getting workstations sized for M&E workloads could be tough. Getting the right GPU, getting the right software, and managing the stack that a studio might have on one of those cloud workstations can be tough. So looking forward to talking more about that as you go on.
That's great. Yeah, absolutely. Yeah, the software lifecycle challenge still exists. It's just a slightly different form, and I think it can be managed a little bit better with the technologies and modern methodology. So, okay. So I think that's a good parlay into modern methodology. What is modern methodology exactly, and how is it used for code, for cloud? So we like to sum up modern methodology as everything is code or infrastructure code with a CI/CD pipeline. Using infrastructure code has a number of benefits. One of the benefits, and I think is one of the most important benefits, is the consistent interface for engineers to build and maintain an environment. A consistent interface reduces friction for the engineering team. The engineering does not have to log into a cloud console or SSH into a server or log into a web UI for the application. Each of those operations costs time and mental energy. It's called context switching, and that can create friction for the engineer if they're having to manage a full stack, which is basically how systems administrators operate these days. So you go from network all the way up to application and user. So the ability to manage configurations, apply changes, modify, deploy the infrastructure through a single interface, in this case, the code, clears the engineer's mind to better focus on what they're actually trying to do, whatever change or upgrade or they're trying to do. Furthermore, the engineer or engineering team can review the current configurations very quickly and rapidly via the code that deployed it, and have a logical, consistent flow when they're analyzing a problem. They can see things in the code that might not be as readily apparent because they're buried in a menu or are a sub-configuration item of something that they're looking at, and they don't see it explicitly called out. But if they have the infrastructure code that created that resource, that service, then they're able to step through that line by line, refresh their mind on exactly how it's configured, and go from there. This style of workflow enables a rapid iteration and review cycle, a rapid assessment cycle, and a rapid change cycle. So engineers, either single or multiple team, can propose a change, review the change, apply the change maybe to a test environment, and then apply the change to production. And that type of cycle is measured in minutes or hours as opposed to days or weeks. And so that reduced friction enables increase in pace for the engineering team. In essence, modern methodology enables the engineer to use a single pane of glass, which is the infrastructure code. There won't be anything outside of the infrastructure code, ideally, that the engineer hasn't been involved with, and having the trust in the code as well as the experience and the time with the code, they're going to know what changes need to be made and what they need to do to move to the goal that they're looking to get to. The other benefit of using infrastructure code and the aforementioned review process is that it moves engineers into a industry tested software development review practice. So when combined with the mandatory use of version control software, Git, engineers can branch, they can review, collaborate, and then eventually merge their code back into the main line of the infrastructure code. Engineers and supervisors and non-coders will be able to actually monitor the progress of either a feature or a change. They can review the history of that change. They can review notes for the commit for that change. And that, again, keeps the friction out of the project and enables engineers to empower themselves to see either, like I said, the history of an item, where an item was, where it is, and where it needs to go. And this is a software development workflow, and it benefits the engineering and systems administration team and the organization as a whole because of the better visibility and better collaboration.
I think it's a really important thing to focus on, Nick, just really quick, because I know a lot of times people are making changes to switches or servers, and even if they go through a change review board of sorts, there's a little bit less scrutiny around the exact changes that are being made at a code level. So I think that it's really important to understand that, you know, if you look at some of the major outages that we've seen for some of the big web services, this is why, right? I mean, we're seeing people push code that has flaws in it, and it's taking out large swaths of, you know, pieces of the internet or services. But I think, you know, it's, while those are high profile and while those are obviously a huge problem, I think without that kind of change review, without that infrastructure as code, you're going to see even more of that, right? You see many times more issues and incorrect config changes out there than you do with this. So it's important to note that having this as part of that change control process brings more people to the table and allows them to review the code in a way that you wouldn't be able to just on a kind of tech by tech basis, making changes to machines.
Yeah, absolutely. I look at this process in addition to a normal or sort of a legacy change request or review process. This closes the loop on the request, the analysis, diagnostic of that change, the proposed change, and then back to approval. And if that circle is complete, then you can either kick that change into the mainline branch, merge it, and have it automatically deployed, or have the engineer deploy it manually, meaning running the code themselves. And that's really a function of how advanced the environment is, or how big the team is. You know, single engineer manage solo, manage the code base, manage the deployment, whereas a team of engineers, you're probably going to want to have some automation to automatically run deployments for changes in the main line. But the use of the infrastructure code will call out in a very clear, and I mentioned this later, in a very clear, it's called a diff. It'll show you before and after. And so you can see exactly what configuration items are going to be changed, what they were, and what they're going to be. And that connects the request to the change, proposed change, and then ultimately you would have a record of that change in your CI/CD pipeline. And so marrying all those together closes the loop and gives the team more confidence, more reliability. Stakeholder sees the change, everyone gives it a stamp of approval, and if it goes right, everyone's in a good spot. If it goes wrong, everyone knows exactly what was changed, and a rollback can occur, or another change request can be on top of it, and you can bring it to the state that it needs to be. So definitely Git, infrastructure code, CI/CD pipeline are necessary to, in our opinion, to do cloud at all correctly, but also to scale and grow in the cloud. So you know, there's going to be the larger infrastructure providers definitely use that, as Jason was mentioning. They use that practice. They pair it with microservices and other container technologies like Kubernetes or AWS ECS or things. And so putting these all together allows that rapid iteration. You know, the infrastructure providers, have gone down because of these issues, but usually back up and running within 30 minutes or an hour, usually. And so that shows that they are able to rapidly diagnose and get their next change out. It's not days until the service is back up and running. And that's really the key with this, is that you're enabling rapid iteration. You fail fast, you succeed fast. So
yeah, and the change is the documentation of the change itself, right? So
exactly. Yeah, the paperwork, the tickets, the code changes in version control can all be associated together. And so you would open up a ticket for a change request, and you would have a description of the problem. You'd have who worked on it. You'd have comments like a normal ticket system, but then you would also have code references. And so in your code, you can reference that ticket number. And so the ticket software will look at the code and say, oh, this belongs here, and it'll give you a preview right there in the ticket. It's called dereferencing, and it will show you what changes were made and how that's associated with the ticket, or what comments were made by the engineer when he edited that code. So that, I think, takes care of what the modern methodology is. We did touch on some of the other aspects of modern methodology, but how does it enable better management? So modern methodology, infrastructure code, and all the associated components does several things. The consistent interface is something that was mentioned earlier. We're going to use infrastructure code and a CI/CD pipeline, and this can take many forms. Some are more advanced than others. The code can be in one or more languages. It's really a matter of the engineering team, with the ultimate goal of reducing that friction. You reduce the friction, and engineers are going to be able to do more. They're going to be happier. They're going to deliver, and they're going to be able to also adapt to changes, because we all know that no IT environment is static. They will be static for some time. They will be set, but changes are going to have to happen, whether it's a business goal, a technology goal, or maybe some artist's goal. Maybe they need a new service, a new plugin. And so we want to make sure to reduce that friction. We mentioned this before as well, is that we want to have an effective review process. We want the changes to be obvious. We want the changes to be auditable, and having the immutable work history that I'll mention in a minute will give the stakeholders, supervisors, and the engineers themselves the ability to do that effective review. The ability to test and commit and review code is also a key enabler of better management. So when you have infrastructure code, you can apply that infrastructure code to, first, your local environment. You can test in local virtual machine setup. Maybe you have a Vagrant setup, which we'll mention what that is. And you can make sure that your code and the configuration that your code is creating is functional. Then you can merge to a development environment and have a development environment deployed using the same infrastructure code. That gives you another checkpoint. From there, maybe you have a double approvals required. Maybe you have a certain test that gets run that says, yes, the service is behaving correctly. And there can be a review cycle there. So at that point, you've already exercised your code 2 times or more, probably many more times. And from there, you can then push your code to the main line and deploy it in production. As mentioned in the last section, the immutable work history is really, really important. So in a version control software, it's called a commit for a reason. It's attached to a SHA, a hash of your commit. It's a unique ID, and that gets layered on top of the existing code base. And I can commit and make changes, Jason can commit and make changes, everyone can. And we can track every file, every line, every piece of code that's in that code base, and we can refer back to it over time. So there's times where you go back to a feature and you haven't touched it for several months. You look at the code that's associated with it. You can look at Jason's comments, you can look at his commits, you can look at mine, you can look at another engineer that may have moved on to a different department or different project, and you can see what they were thinking, why they committed what they committed, and review their history to, again, get your head in that right space. You don't have to necessarily go talk to them. Maybe you also bring it up and they use that same immutable work history to refresh their mind. and that gives you the ability to track that work over time, unchangeable, and that can be used for a number of things. In addition to what I mentioned, things like audits. The diffs that I mentioned earlier are, diff is a short for difference. It's a way of showing differences between two files. And if you have a work history that's tracked, you can diff between every different version of that file over time, and you can recreate very quickly in your mind what the history of that file, feature, or service was. And so if you have to go all the way back to the beginning, you can. If you want to start in the middle, you can start at the beginning and rewind, and you can see what the changes were made. And that feature alone has paid dividends for us in almost every situation that we've worked with in the cloud, whether it's a change that had an unintended effect, change that needed to be made, that we needed to unwind some complexity. The ability to rewind the code history has been is very, very, very powerful. And with cloud, as is the topic of this webinar, we're going to have quite a bit of complexity, which we'll show in the next few sections here. And the engineer needs to be able to clearly understand all of those nuances and configuration points, as we call them. And so we like to introduce the infrastructure code sooner rather than later. If you introduce infrastructure code now, you're going to start putting time and effort into maintaining it, understanding how it works, and that will pay dividends later at likely an unexpected time. So we want engineers to use infrastructure code right away. We introduce it right away. We create a fresh repository for the project or the customer, and we start writing code right away. And sometimes that's pseudocode. You know, there could be a design cycle that needs to occur. We can apply the same principles, the iterative design, with the modern methodology to pseudocode or light documentation or brainstorming session as well. We can create a text file, store the text file in version control, and over time that text file is going to evolve into actual usable, executable infrastructure code. So. Jason, do you have any comments or questions for?
No, I think it's worth pointing out that a lot of people are probably familiar with this in a software development cycle, and what we're talking about isn't necessarily new in that regard. It's more we're now taking this and applying it to everything else, right? So everything from the project kind of design and management to the switch configurations, server configurations, workstation configurations, and then sort of the meta configuration of all of those things, right? Like how are we going to deploy all of these servers? How are we going to deploy all of these workstations? So it brings all of that same immutable copy and immutable tracking to what we've been doing as systems engineers and network engineers in a little bit more of a manual fashion over the decades.
Sure. Yeah, absolutely. I agree completely. There's sort of a cultural transformation that occurs with that, because from the systems administration, on-premise infrastructure, sort of legacy infrastructure, to the modern methodology in the cloud is really not as complicated as some may think. Really, you just start, and we can help you start. We can give you those first steps, and we will. We sort of already have, but just start using infrastructure code. And as Jason said, infrastructure code is not exclusive to cloud. We believe that it is mandatory for success in the cloud, which is why we're here talking to you today. Without it, you will wind up with sprawl, and the infrastructure in the cloud with the combination of your on-prem will spiral into a form of unmanageability. That can manifest in a number of ways, either complexity and unexpected problems, it can be cost sprawl, or just the inability of new engineers or any engineers to get in and make changes confidently. So we definitely recommend getting the infrastructure code started sooner rather than later, and that will then help with the adoption of cloud. Jason, do you have any comments before we move into virtual desktop?
No, please go right ahead.
Great, awesome. Okay, so what does a virtual desktop infrastructure actually look like? And so here we have a architecture diagram. This is something that we like to do at the start of a project. This, what you're looking at, is the result. We actually went through several iterations with this customer, and there were requirements that were called out from the beginning that changed, and then there were unknown requirements that were discovered through the process of the design. And so applying the iterative design principle to the architecture and to the design, this is what we wound up with. And so I'm going to go through the components from the perspective of what we can see and what we can't see, and then we'll move on to how we manage those things that we can and can't see using these modern methodologies. So this is a diagram of what a production virtual desktop infrastructure actually looks like. And this design is implemented. This design is used for a multi-production studio, and this design actually supports multiple productions as well. So we have the user over here. We have their workstation. Then we have their connection to what's called a LeoStream gateway. LeoStream is a connection broker for virtual desktop. This is a server running a certain operating system, certain specifications, and a public IP address. Next to it is what's called the Teradici Connection Manager. This is used to support the actual Teradici protocol. So this is specific for Teradici. It's a server with a certain set of requirements and a public IP address. Both of these servers are public facing, and they have a certain security group on top of them, and the ports are listed over here. Behind that, we have Active Directory and a private service over here. That's represented by a server, no public IP address, it's private. And then we also have the LeoStream Connection Broker, which is sort of the second half of the LeoStream solution, and that's responsible for saying who gets to connect to what, where they get to connect, and where they should go to connect, and so on. So there's a coordination through the LeoStream API. You can see there represented. It's over HTTPS, port 443. Then we have the actual connection from the broker to the workstation, which is for coordination of, is the user session available, is the workstation on, is it running Teradici, does it have a license, those sort of things. Then we also have the connection itself for the PC over IP traffic flowing from the Teradici Connection Manager back to the stations. And so put those all together, and you can do a virtual VDI from the user anywhere. They can connect into a public SSL encrypted. They're authenticating using their Active Directory credentials. In this case, they actually have Okta on top of it, so a single sign-on, which it introduces a little bit more complexity. Teradici Cloud licensing, which is just an external connection to Teradici. And then, of course, you have your Avid. In this case, it was Avid, but any workstation or storage can apply. And you see the Avid storage behind it. And those aren't really covered, but they're on the document for illustrative purposes. So we can see all these things. We see there's a server responsible for carrying Teradici traffic. We see a server responsible for LeoStream connections. We see a server for authentication of users. We see a server responsible for Active Directory. We see the virtual workstations mounting the storage. We can also see here, we see a virtual network, which is represented by these gray boxes. We can see subnets, which is similar. We see public IP allocations, which are mentioned. We see security groups, sort of. We see the call outs of what the actual protocols and ports are. We see a resource group, in this case is Azure. It's up here at the top. It's blurred out for privacy reasons, but all this is wrapped in a resource group in Azure. We see virtual network interfaces, 1, 2, 3, 4 technically here. We see virtual machine specifications, and we see virtual machine OS. Okay. What we can't see are things like installation binaries for this LeoStream connection broker. How do I go from CentOS 7 to a functional LeoStream connection broker? How do I go from CentOS 7 to LeoStream Gateway? And how do I go from CentOS 7 to a Teradici connection manager? Those details are not on this design. Those are implementation details. We don't see installation commands. We don't see SSL certificates. We also don't see any application configuration files. So these servers don't necessarily just run out of the box. You have to configure them, which is normal for what we do. But that is not going to be captured on an architecture diagram. It's too much detail. It's too low level. It doesn't really have a place on an architecture diagram. It's sort of, if it was on an architecture diagram, it would almost be a waste because the configuration could change. Maybe that configuration is for one environment, but there needs to be another instance of this, another deployment of this solution. And having the configuration files on a document like this doesn't really do the engineer much good, because they're going to have to basically just copy paste it into another location, do the configuration manually, and now we're just back to doing things the old school way. What we definitely can't see is application specific configs. We have no visibility on the licensing, and we definitely can't see those SSL certs or certificate CSRs or anything like that. So, architecture diagrams are very important. They have to be done. We do them for every job, but they're not everything. They're necessary, but not sufficient, meaning that there's going to be gaps. And so with the understanding of what this needs to ultimately look like, that's how we can get into tying modern methodology in with what we need to do, which is created by the design. Now we can turn over to the implementation side. And so how do we use a modern methodology to manage all of these aspects? We have all of the aspects that we illustrated, all the necessary components for a virtual desktop solution, but what do we actually do to make it from the abstract design to reality? Well, we code it all. So what you're looking on your screen here is a Git repo in a web application. This is hosted in Azure DevOps, but GitHub, Fabricator, GitLab, all of those are solutions that do essentially the same thing. They provide a web interface for engineers and supervisors and everybody to do all the things that we mentioned before: review, audit, simply view, even edit code. And so you can see here, this is a folder that's been instantiated in a Git repo, and a Git repo has some files, git ignore, and has a .git folder, but that's not displayed. This code repo has everything that's needed to deploy this solution. So every one of these components that you see here, with the exception of the user, is going to be captured in the code repo. And so for this deployment, we actually used this code repo, coded once, and built a local version. Tested it, everything was working great. Then we moved to a testing environment, and that testing environment was in our cloud. It was public. We had users test it. We had the customer test it. They said, yeah, it looks great. It's working great. Everything we expect. And then from there, we actually moved it to the production environment. And so having the exercising of the code, plus the tracking of the code, plus the delivery of the code, and actually in this case, we took this code repo and we moved it over to the customer's environment, and the customer executed the code. And so as a service provider, we're able to deliver the solution without ever touching the customer's environment, which is very powerful. The principle of not touching production and only interfacing with production through code is very powerful, because it prevents a lot of problems from occurring. If someone goes into a production environment, makes a manual change, no audit, no review, no code history, it's a ghost problem. And so we were able to even take it a step further, and we didn't even execute the code, the customer did. So this code that you're looking at here manages everything, and we're going to go through here in the next slide some of the specifics and key parts of what the code has. So you just flip over, do a little, actually before I flip, I'm gonna just do a cursory on what these scripts are and what they do. One of the key files here is azure.yaml. This is a playbook for provisioning all the Azure side components. So starting from the resource group down to the subnets, to the network interfaces, servers, public IP addresses, network interfaces, security groups, anything Azure side, this playbook configured. It's about 450 lines. So some may say it needs to be broken up into multiple files. That's definitely true. There's about 75 configuration values for Azure alone. So if we flip back to this, we look at this, we see, okay, an Azure subnet, a few Azure components, and that's it. You only see 3 or 4. But when you get down to the actual implementation, you'll find that there's much more detail than any architecture document could show you. And so this file here, again, 75 configuration values, and we'll show some samples of what those look like in a moment. There's also the Azure VNet here. So this customer needed to support multiple productions in multiple regions, and they wanted to connect all the resources to central management for the VDI and have some users share VDI, and some artists worked with multiple productions and needed to access multiple VDIs. And so we decided on a VNet peering for them. That's not included on the architecture diagram, but this playbook actually will peer to Azure VNets for you. And so you set up a couple variables, source and destination, and run this playbook, and you'll wind up with a VNet peering at the end of it. So that was kind of a value add for the customer towards the end of the project, but it is a separate playbook because it's not mandatory for the initial deployment or deployment of the VDI solution in the core subnet. Then you have the deploy.yaml. This one is more on the application side. This is about 220 lines and has about 40 configuration values, and this is for deploying the application itself on top of the Azure infrastructure. And so between the two already, we have 130 or so configuration values, and that's a lot for anyone to manage. In my opinion, a solution like this would take a team of people to implement in the past, but now it can be done by one person or less, maybe a half day or much less time than a dedicated resource to manage the VDI service in the cloud. It can be managed as just a small part of what a team does. And that's by virtue of all the details and all the heavy lifting is captured in the code. And we also have a README file. This is markdown.md, standard developer style documentation, simple, text-based, has bootstrapping information, has dependency information, tells what the code will do, what it won't do, and it also has information for the local environment. Local environment is represented by what's called a vagrant file. Vagrant is a technology that allows you to manage one or more local virtual machines and quickly tear them up and spin them down. Very useful for testing. Was born out of development workflow, so software developers needed to build a stack and build their application. They would do that in a development environment locally, but we can apply the same principle to systems. If I need to deploy a server, I can spin up the base operating system and run my automation against that local machine. If it fails, I can tear it down and fix my bugs and rebuild it from scratch. And so just by virtue of me spinning up the environment and tearing it down regularly, I'm exercising my code and making it stronger and more robust. Each one of those cycles occurs. You also see here we have a license file. So this is provided by the vendor, and we drop it into our repo. And in the deploy.yaml, there's actually a line that takes this license file, it places it on the server where it needs to be. And so now we have our license tracked. It can be encrypted in the repo for security reasons, and the code can decrypt it and push it to whatever server it needs to be on, or multiple, and put it in the correct place. We have templates, which is files that have variables inside of them. I think we have an example coming up of what that would be, but you can think of any configuration file on a server. This needs to be filled out and doesn't come with the information you need. You can use a template, and that'll allow you to have a base, and then you can have variables. Common variable is like a URL. So if you have multiple deployments of an application or just one, you want to have the URL set to what it actually is going to be for that application. Or say you have one service, but you want to have that service in a test environment. The test environment is going to have slightly different parameters different IP, different URL, maybe even a different license. And so you can use template files to push those out. So, and then we have, of course, our SSL certs and our CSRs, which you can see here. Useful storing those in version control because certs can be somewhat complicated. You sometimes have to convert. Sometimes you have to put them in multiple places. Concatenate them together, put them in a place, convert them to not PEM to a different format, things like that. And you can have your infrastructure code do that, but still keep your source of truth here with the SSL, with the files actually in the thing. So moving on, I'm going to try to move a little quick here. This is what the code actually looks like. So we can see on the left side here, line 2, we go Azure get all facts from resource group. In this case, we had a resource group already in place, but it's very similar to create one. We also see here some commented out code for creating the virtual network, adding a public subnet, and adding a private subnet. And you can see each of these has 4 variables or 4 parameters that need to be passed. Private sitter, short names, which is like a code name, and then a name for the resource and the resource group itself. These all would have to be entered manually by the engineer, and doing it manually is how you wind up with inconsistencies or errors or oversights or other things like that. So these variables are populated in what's called an inventory file in this configuration management language, which is Ansible. There's others. They all support a very similar pattern of having inventory and variable precedence, so you can assign variables based on what you're deploying against: dev, test, production, those sort of things. So this is an example of what you would use to build a basic Azure subnet here. At the bottom, you can see there's a creation of a IP address for the Teradata connection manager. This is the public IP address we mentioned. And again, there's more parameters where it needs to go. You can choose an IP sort of out of a pool, or if you have one, you can reassign it, do things like that. In this case, you're just assigning a new one. This block that's highlighted here is, I believe, line 201 or so in the same script. So once all these resources are in place, you could see you can move on to actually creating a VM, which is sort of one of the most obvious things that you can do in a cloud, is create a server. And so you can see here, 1, 2, 3, 4, 5, 6, 7, 8, 9 configuration values for just the VM. And so that's what was referenced earlier, is the 75 is every resource isn't just create that resource. There's all the associated values that need to be passed correctly to the resource. So you can see here, there's a key pass to it. There's the NIC that's assigned to the network interface, the operating system that's chosen. And this is a good example of, say, there needs to be an upgrade. You can use this as a base. Okay, I'm starting CentOS version 7.5. I can spin up a machine next to it. I can apply my code to that new machine, and so on and so forth. So you can also see here a sample of what a network security group looks like. Network security groups can be very complicated, not in concept, but in implementation, simply because they might have a lot of values. And so in this case, this is just an example of allowing SSH. There's actually about 8 rules below this as well that just didn't have room to fit on, and just wanted to show everybody what the security group looks like. And each server has a security group, so there's one of these for every server, and each of them has a slightly different set of rules. And so everyone on this call probably knows, TPN doesn't like things that are publicly accessible. They don't like things that are open to the world, and they don't like things that have ports open for services that aren't necessary. And so the ability to atomically control every server, every security group, every port, every service is vastly enhanced by using infrastructure code because of the granularity and the explicit call out of everything. You run infrastructure code with no configuration values, nothing's going to be configured, nothing's going to be open. Once you start adding configuration values, you know what you've added, you know what you open, and again, the engineer is going to have the confidence about their environment. This is the VNet peering. This is more interesting than complicated, but you can see it's essentially initiating a VNet peering on resource group 1 and then connecting the VNet peering on resource group 2. And so, to do a VNet peering, you have to basically do an inverted config on both sides, and that's what this code represents. You run this code, it'll update the route tables for you, it'll create the route table, update the route table, and when this script is done executing, you'll see a VNet peering. Take us a minute or two to initialize, and you go from there. So again, this is all Azure side here. This is the application. So you can see we just went from code with Azure Virtual Network related, then we went to virtual machines, security groups for them, we did some VNet peering, and now we're moving into the actual application deployment. And so in this case, on Azure, we're just deploying LeoStream Gateway. We want to install some basic applications. We're going to install the Teradata Connection Manager, which requires some source directory. It requires the downloading of a file of a certain version. Requires an archive. It requires setting the mode of that file to have execution, and then actually running it. And so that process, while it may feel or sound somewhat trivial, is complexity. 1, 2, 3, 4, 5, 6, 7 steps. And that's just for one of those 3 services. And this also doesn't include the configuration of it. So here we have an example of using the same infrastructure code. I'm going to flip back. Looks the same style, same syntax, same color, same window, same interface for the engineer to do the infrastructure below Azure, to do servers, and now they're at the application layer. So this playbook here actually will deploy everything. This was the deploy.yaml file mentioned earlier, and this has 3 additional sections like this with the totals of what we mentioned earlier. It'll create the source directories, download the application, archive the app, unarchive the application, run the setups. Then it will also copy SSL certs. It will pull copies of the local configuration files just for review purposes. Then it will also template and configure, which is what you're looking at over here. You can see right on line 9, there's a PC over IP address and a variable that says broker IP. This is of value, as I was mentioning before, that would need to be changed for each implementation. And so we store that value in a variable for the environment. When the code is run, it will pull that variable and deploy. It'll also do some silly things like reboot the server and wait for it to come back up because you want to test some services, make sure your services are enabled and started. And then also, as part of this environment, we needed an Active Directory server for our test, but production already had it. So we actually have a playbook that deploys an Active Directory server for us, which is pretty nice. So this is the end of the line in terms of the implementation, because after executing this code, we're going to have an instantiation of our designed architecture solution for virtual desktop. So we're going to have the 3 servers that we mentioned. Go back to it. We're going to have this server configured. We're going to have this server configured. We'll have this server configured. We'll have an Active Directory server configured. And then from there, we have an up and running solution. Jason, you want to, do you have any
Yeah,
comments?
I mean, we're actually kind of blowing past the top of the hour here a little bit, so thanks everybody for sticking around. I know some folks are having to drop off, but I mean, it's great because, you know, at the end of the day, you've got a recipe for building a studio in the cloud in essence, or not even necessarily in the cloud, but you have a recipe for building a studio upon infrastructure wherever it may be, regardless of what it may be, and it's going to be consistent wherever you deploy it. And I think that's really kind of the key here, right, is the portability and the scalability and the reliability of the implementation side of it. So it's really a powerful way of looking at things and maintaining things and scaling things as you move between working private and on-prem and off-prem equipment.
Yeah, absolutely. I like to look at it quite simply as 0 unknowns. Every piece of the infrastructure is captured in the design and in the infrastructure code, and that is immensely powerful for a single or a team of engineers.
Is there anything that you want to close on? Let's respect the folks who are here in their time. I know they probably want to hear anything that might be coming at the end before they drop.
Yep, just recommended reading. These 3 books have basically changed my life. Linux System Administration Handbook, not necessarily pertains to VDI or cloud, but just Linux system administration helps with understanding a lot of the paradigms that we deal with. The practice of cloud and system administration, Tom Limoncelli, he co-authored this book, which is DevOps and Site Reliability Practices for Web Services, slightly different working with systems at scale or in the cloud or that are distributed, which applies to multi-region studios, studios that are running applications in the cloud and so on. And then finally, time management for systems administrators, which isn't specific to DevOps or cloud, but it's useful because there's several practices in there like tickets that are called out as mandatory, and having those in place for a system administrator vastly helps with their cloud practice. So,
Nick, awesome. This is great. Thank you for walking through all this. I love stepping through code with you because I love that you comment everything perfectly and you know exactly what everything means all the time. So it's always fun to do that kind of code review with you. Thanks everybody for showing up. You know, we're going to be doing a lot more webinars like this. If you'd like to come and you know, basically join us as we step through the processes that we take with our customers, and you know, hopefully can do for you at some point. We would love to have you. If you have questions about this webinar and you'd like to discuss these topics more, please feel free to reach out. You can contact me directly if it's a technical question. I love talking about this stuff. Just jason@gpltech.com. If you have a sales related question, please feel free to reach out to sales@gpltech.com. We're here to help you guys. We love doing this. We live this every single day. So please let us know if something we can do for you. And again, thank you so much for showing up today. Nick, thank you. And hopefully we'll catch you guys next time.
My pleasure.
Thanks everybody. Have a great day.